It's a pleasure to have you join me on this virtual journey. Welcome. We're thrilled to present to you our video dedicated to faithfully flat descent. Enjoy. Faithfully flat descent or flat descent is a technique from algebraic geometry, allowing one to draw conclusions about objects on the target of a faithfully flat morphism. Such morphisms that are flat and surjective are common, one example coming from an open cover. In practice, from an affine point of view, this technique allows one to prove some statement about a ring or scheme after faithfully flat base change. In the language of stacks, flat descent is exactly the statement that the prestack of quasi-coherent sheaves is a stack with respect to étale or topology. Vanilla faithfully flat descent is generally false. Instead, faithfully flat descent is valid under some finiteness conditions, e.g., quasi-compact or locally of finite presentation. A faithfully flat descent is a special case of Beck's monadicity theorem. In the upcoming section, we'll be dissecting the idea and exploring its intricate connections to our topic. Given a faithfully flat ring homomorphism B, the faithfully flat descent is Rowie, the statement that to give a module or an algebra over A is to give a module or an algebra over B together with the so-called descent datum or data. That is to say, one can descend the objects or even statements on beta provided some additional data. For example, given some elements F are generating the unit ideal of a B is faithfully flat over A geometrically. The operatornum spec big I equal R operatornum spec is an open cover of spec, and so descending a module from beta would mean gluing modules mi on A to get a module on A. The descend datum in this case amounts to the gluing data, i.e. how mj identified on overlaps spec. As we venture forward, let's examine a fine case in detail and gain a deeper appreciation for its significance. Let A be a faithfully flat ring homomorphism. Given a module M, we get the B module NM_ab, and because a B is faithfully flat, we have the inclusion MM_ab. Moreover, we have the isomorphism of Rphi, no times both sits into no times B of B2 modules that is induced by the isomorphism B2 XYYX, and that satisfies the classical condition, where of Rphi, no times bo times I over sits into no times bo times are given as NBC urban C, NBC urban C, NBC with EXIYREI1XYER. Note the isomorphisms of Rphi, no times bo times I over sits into no times bo times are determined only by and do not involve M. Now, the most basic form of faithfully flat descent says that the above construction can be reversed, i.e. given a B module north and a B2 module isomorphism of Rphi, no times both sits into no times B such that an invariant submodule Mn and 1Nn is such that Mbn. Here is the precise definition of descent datum. Given a ring homomorphism B, we write D Bn1 for the map given by inserting a B in the ith spot, i.e. is given as Bn_ab Nb_ab Nbn1, as Bnb Bn1 Bn1, and so on. We also write Dn1 for tensoring over Bn when Bn1 is given the module structure by D. Now, given a B module north with a descent datum, define M to be the kernel of Nn derved 2. Consider the natural map Nbn X-axis. The key point is that this map is an isomorphism if a B is faithfully flat. This is seen by considering the following. A binary local 0 to and mo times a B to quad no times a B a right arrow of Rphichict and no times bo times O times a B and down arrow and of Rphichict down arrow and quad down arrow of Rphi times bo times a circ 0 to and north to quad no times bo times a right arrow and no times bo times I and array, where the top row is exact by the flatness of B over A and the bottom row is the Amitsa complex, which is exact by a theorem of Grothendieck. The classical condition ensures that the above diagram is commutative. Since the second and the third vertical maps are isomorphisms, so is the first one. The foregoing can be summarized simply as follows. Brace yourself for an in-depth analysis as we navigate through Zariski descent and its far-reaching implications. The Zariski descent refers simply to the fact that a quasi-coherent sheaf can be obtained by gluing those on a Zariski open cover. It is a special case of a faithfully flat descent but is frequently used to reduce the descent problem to the affine case. In details, Cohax denote the category of quasi-coherent sheaves on a scheme X. Then Zariski descent states that given quasi-coherent sheaves Fi on open subset UI X with X UI and isomorphisms of Rph Fiu equipujovacit sympto Fju equipuj such that one ided and two I on UIUJUK, then exists a unique quasi-coherent sheaf Fahrenheit on X such that Fui Fi in a compatible way, i.e. Fuj Fj restricts Fu equipuj simac Fiu equipujovacit Rph undersit sympto Fju equipuj. In a fancy language, the Zariski descent states that, with respect to the Zariski topology, a co is a stack, i.e., a category equipped with the functor P, the category of relative schemes that has an effective descent theory. Here, let a co denote the category consisting of pairs U, F consisting of a Zariski open subset U and a quasi-coherent sheaf on it, and P the forgetful functor U, Fu. Let's now turn our attention to descent for quasi-coherent sheaves and uncover the fascinating insights it brings to the table. There is a succinct statement for the major result in this area. The prestack of quasi-coherent sheaves over a scheme south means that, for any S scheme X, each X point of the prestack is a quasi-coherent sheaf on X. The proof uses Zariski descent and the faithfully flat descent in the affine case. Here quasi-compact cannot be eliminated. Get ready to immerse yourself in the world of example, a vector space as we examine its impact and relevance. Let Fahrenheit be a finite Galois field extension of a field K then, for each vector space V over F. Vkfov via Eov where the product runs over the elements in the Galois group of Fk. As we embark on the next leg of our journey, let's unpack the layers of étale descent and examine its core elements. An étale descent is a consequence of a faithfully descent. Now, let's dig deeper into via the monadicity theorem and unveil the hidden treasures it holds within. Let F, xy be a morphism of schemes and F denote the push forward as well the pullback for quasi-coherent sheaves here, for simplicity. Assume F key is well defined. Since F is a left adjoint of F, the composition T together with the canet and the multiplication induced by the adjunction is a comonad. Then Beck's monadicity theorem, if applicable, says that the functor F T-colg is an equivalence, where T-colg is the island of category of T-chi algebras, i.e., roughly, the category consists of objects in Cohax with T-coactions at F. Despite the name, they are more like comodules than chi algebras. Then the key point here is that a T-action amounts to a descent data and thus T-alg can be identified as the category of quasi-coherent sheaves on X together with descent data. Hence, the above exactly states the flat descent. For example, if F is a faithfully flat morphism between affine schemes, then the monadicity theorem applies and the above recovers the flat descent in the affine case. More generally, the theorem applies if F is faithfully flat and has some finiteness property, e.g., a morphism. Share this video with your friends and spread the knowledge.